Okay. I think, oh wow, that's a lot of people for a tutorial. Let's see. Are we more or less than 10? So I printed the problem sets. I printed 10. That was my prediction. How often is that? Right. Okay, you guys want to share? Let's share. I do not. Oh, okay. You guys share? Okay, nice. Okay. Right. Right, we're playing on the road. No, no, over here. Right, so I think we can get started. So hello everyone. Um my name first of all, this is the tutorials for Comp 330. So this is tutorial 1 and the date is the 4th of September. Yes, so right. Hello, my name is Cesare. So this is my name. And then this is how you pronounce it. Cesare. So hopefully you know all about arrays, but this isn't too much of an abstract concept for you. I'm a PhD student here at McGill. I work with Jackie Chung. Is anyone taking the AI class? Nice. Okay. So you'll say hello to Jackie for me. Nice. Next time. Okay. Yeah. So I'm a PhD student with Jackie, and I mostly work on natural language processing. So the language part is why I typically TA or teach this class. Um, and I've just to give you a bit of background to convince you that I know what I'm doing. I did a quick calculation, and this is my ninth time TAing this class. Uh, so that made me realize I'm no longer very young. I've TA'd it 6 times at McGill, and then there's a similar version of this class at Concordia, so I TA'd it 3 times there. Um, And I really like teaching, and I really like this class. Bless you again. Although maybe it wasn't you who sneezed last time, but anyways. And so that's why it's always very fun for me to teach or to TA this class. Um, I was talking to some professors, and they were saying how they were sort of dreading the start of the semester because they can't do as much research. And when they said that, in my head, I had the sort of exact opposite reaction. I was saying, oh, I'm excited so I can teach, so I can do less research. Um, so it's a bit of a different perspective on things. Um, okay, so that's maybe enough about me. You already seem very bored, so I'll skip more intros about myself. I think you might have had this question. So what is the sort of goal of the tutorials? Uh, the goal of the tutorials is essentially really just to solve the problem sets. And the goal of the problem sets is to prepare you for the midterm and the final. I guess it's midterms plural. So we decided this semester to not do assignments. There's a bonus assignment, which is sort of going to count for extra credit. But yeah, with last semester, we sort of started noticing that like a quarter to a half of the assignments were just ChatGPT. So yeah, it's a bit unfortunate. I would have liked to have assignments because I think they're like a good way to increase confidence and so on. But I think instead, this is like the best alternative we could come up with. The problem sets which I've handed out are going to be a very good approximation of what's going to be on the midterm. I'm going to be, as far as like TA's goal, I'm going to be very involved in terms of like designing the midterm, much more than TAs in other typical classes. So when I say that something is, probably good to study or, good to review or whatever, then I'm saying it for a good reason. Yes, one a week. Yeah, so like 12 or 13. Yeah.
Like since there are six problem sets, so
Yeah.
approximately how many questions will you be able to cover in the
Aha, yes, that's a good question. So I will, very, very nice. So I will solve some of the problem set questions, and not all of the problem set questions. I'm going to solve the ones that I think are extremely relevant. This is not to say that the other questions in the problem sets are not extremely relevant, but the ones that I'll present are maybe more so. I would say also that that's the reason why there's so many office hours. So we've been able to sort of take all the time that the TAs spend for grading the assignments, and now they're sort of converted to office hours. So if you want the solutions to some of the problem sets then that aren't covered in the tutorials, then you can talk to the TAs, who should have like been able to solve the problem sets because we like sort of talked to them beforehand. Yeah. Sorry, sorry. No. No. So there's no, as of right now, we're not planning on releasing solutions to the problem sets. Yeah, yeah.
Like will the tutorials be recorded and
Yeah. Yes, they're recorded. Yes, yes. And I'm gonna post the notes.
the solution?
Yeah, what I'm gonna write. So it should be okay. Okay, good. Any other concerns? Fears? Okay, because I was talking to someone who was debating whether they should take this class or not, and they were kind of scared because they were like, "Oh, there's no assignments; it's just all tests." So I can see why, like in theory, that seems scary. Like I would probably also be a bit afraid. Um, but I can sort of almost I can assure you that I will make sure that it's not scary. So so that you're very prepared for the tests and that it's gonna be okay. Okay, good. All right, people seem convinced, so that's good. All right, so on to some material. So I think maybe before I start the actual material of the class, I just want to quickly tell you what's the point um, of taking Comp 330. Because you might be asking yourselves why do you have to take a sort of theory class if you're a software engineer? So the direct and most simple answer is that it's to study the inherent limitations of computation. So there are some things that computers can do, and there are some things that they can kind of do, not super well, and then there are some things that they absolutely can't do. And so this is pretty relevant when it comes to things like AI and sort of large language models. There is sort of a very active field of research right now, which is sort of asking, well, what are the skills and the tasks that language models can and cannot learn? So ideas of like learnability, ability by language models. So the reason why you have to take this is because if you sort of go off to industry or you go to grad school and you just say, oh, well, I can just write an algorithm for anything, then you might get an advisor or a manager who looks at you a bit uh, funny. So it's sort of to sort of try to avoid that. And the way that we're going to try to answer this question, the sort of roadmap for the class, if Jérôme hasn't told you yet, is essentially sort of a three-part series. The first part is going to be about automata theory. So essentially, how do you sort of formally define what a computer is? The second part is going to be about computability theory. Computability theory, which is, well, what is solvable and what is not solvable. And the last part is going to be complexity theory, which you also do in Comp 360. And so that's just like how hard or easy is a problem. Okay. So this is sort of all together is how we're going to be answering the sort of question or how we're going to be convincing you that there are inherent limits to computation. Okay, so that's my spiel as to why I think this course is interesting. Now let's get to some actual problems. So let's start with a quick math refresher. So I'll do only two problems from that section, but I'll do the problems which are the most relevant for you to sort of understand the lectures as well. And also like the questions that we might be asking was sort of assume that you kind of know how to answer this kind of question. So it's useful to get through. Okay, so the first thing that I want to talk about for the math refresher is this notion of sets. So hopefully everyone has a general idea of what sets are. You know, these are collections of objects. So you can think of them as like bins of stuff, right? So, you know, you might have one set, you know, maybe set A, which is the set of even numbers. So this might be the set of even numbers. Then you might have a subset of that set. So a subset is a set which contains all of the elements which is sort of contained within this larger set. So for instance, you might have the subset 2, 4, 8, and so on for powers of 2. Powers of 2. And then you might have, you know, another set which isn't fully contained, so it's not a subset, but it's maybe has some things in common with this set. So maybe like 3 and 12, but also 3 and 9, so multiples of 3, right? So, you know, you have set intersections, set subsets, set unions, and so on. So these are all things that I'm sure you kind of know already about. Now, what's the relation to sort of Comp 330? So in Comp 330, we're going to be doing a lot of, you know, showing that two sets are the same. That two sets are equal. So, you know, showing something like you have two sets, maybe they're subsets of sigma stars, so maybe these are languages. So languages are just sets of strings. And what we want to show, so WTS is short for want to show. What we want to show is that A is equal to B, right? And so then how do we typically do this? How do we show that two sets are the same? The technique that's going to be used a lot throughout the course is this technique of double inclusion. So in double inclusion, essentially what you do to show that two sets are the same is you show that the first set A is a subset of B, and vice versa, that the second set B is a subset of A, right? So, you know, you might have two sets, A and B, right? So at first, it seems like there's things that are different between them, but then this first thing shows that A is fully contained within B. And then the second thing is saying, well, B is now fully contained in A. So the only way for these two things to happen at the same time is for A and B to be sort of exactly the same, right? So maybe a bit more formally. So A is equal to B, if and only if A is a subset of B and B is a subset of A. And this is only true if, so I'll just remind you of how to show that a set is a subset of another. So to do that, right? So how do you show showing subsets? So showing subsets, A is a subset of B if whatever element you take in A, it's also in B, right? So for every element in A, that element is also in B, right? So that's A subset of B. And then vice versa, B subset of A is for any element in B, that element is also in A, right? So that's how you show that one set is a subset of another. And then if you show these two things together, then you show that the two sets are the same. Okay, good. So what's an exercise related to this? So it's going to be from problem set 1, of course, and it's going to be question 3C. So question 3C asks to prove that if A is a subset of B, then this is true if and only if A different B is the empty set, right? So this is the set that contains no elements. Set with no elements. So I'm going to give you some time to solve it, but let me just to try to solve it. But let me just tell you first what this is sort of saying intuitively, because the way to not get lost in statements like this is to first try to say or try to see what is sort of the statement actually saying intuitively, right? So I have two statements, 1 and 2, and I want to show that these two statements are just rewordings of the same reality, right? So 1 is talking about one reality and 2 is talking about another reality. Actually, they're the same thing, right? So to do that, well, we want to show that if 1 was true, then 2 would also be true. And if 2 was true, then 1 would also be true. Now, what are 1 and 2 saying, right? So 1 and 2 are saying, respectively, that, so for 1, A, so some set A is fully contained in some set B, right? So that's what 1 is saying. And then 2 is saying that if you have some set A and then subset B, and what you do is you start removing elements of A, right? So you start removing elements of A if that element is also in B, right? So remove X from A if X is in B, right? So you do this for every single element in A. And then at the end, right? At the end, you get A different B. And it just so happens that A different B is equal to the empty set, right? So what this is saying, right, is that these two sort of realities that I've just presented actually mean the same thing, okay? So now I'm going to give you maybe 2 minutes to try this exercise in case you haven't tried it. And yeah, I can answer if you have a question.
That's solved by cardinality.
It's a bit trickier if you do it by cardinality. It might be easier if you try the way that I'll show you, or yeah, you'll see. Yeah. Okay, I'll give you 2 minutes. Move front of the door. Okay. That means it's been 2 minutes. Time flies when you do subset inclusions. Okay, so how am I going to do this? Right, I need to show both directions of the statement. So I'm going to start with one implies two. So I'm going to assume that A is a subset of B, right? And now what I want to do is I want to show, bless you again, I want to show that A different B is the empty set. So I think a very, very strong, a very sort of common thing that students tend to do is they try to do proofs sort of directly. I mean, it's very possible that you can do this proof directly, but if you do a direct proof, so if you do this directly, then it's very, very, very easy for someone to just say, well, this is obvious, right? And so this is to avoid, okay? So please do not say this is obvious in the midterms, okay? When you do proofs. I know some of the math students might be very inclined to do that, but the graders will be less inclined to give you the marks, okay?
That's the intuition.
It's the intuition, yes. Intuition is great. Intuition is great, especially if it's a true false. Oh, is it true? Is it not true? That's true. I agree with you. The direct proof, so this is a good point, because it's very possible that the midterms have true falses. If I had anything to do with it, then they would. So intuitions are really good for solving true false questions. But if you wanted to do this proof sort of formally, then I think a better thing to do if you don't want to just fall in the trap of, oh, this is obvious, is say, well, assume this is not true for contradiction. So assume A different B is not empty for the sake of contradiction. Okay, so I'm saying that even though A is a subset of B, A different B is not empty, right? Okay, so let's reason sort of from first principles. If A different B is not empty, A different B is not empty, then this implies that there exists some X in A different B. Right? So this is probably a good path to go towards if you want to show this result, because whenever it comes to set proofs, if you just reason from first principles, you're probably going to get to the answer in very few steps, okay? So I reason from first principles that this implies that there exists some X, which is in the difference. So what does this imply? Well, what's the definition of the difference, right? The definition of the difference is, X is in A different B, A different B. This implies that X is in A and X is not in B, okay? But now this should immediately cause concerns, right? Because we assumed initially that A was a subset of B. So what's the definition of A subset B? It means that if an element is in A, then it must also be in B. But what I'm showing here is that that's not the case. So then I have a contradiction. So I have a contradiction, which means that the assumption that I had started with, so this one was incorrect, which means that the sort of negation of it must be correct. So it must be that A different B is equal to the empty set. Okay. So I'll use this symbol for a contradiction because I think it looks cool. And it's slow to write contradiction. Okay, so this is one implies two. So far, so good. Okay, I got one nod. One nod is enough. So let's do two implies one. So two implies one is, I know that A different B is empty. Now what I want to do is I want to show that A is a subset of B. Okay, again, in this case, it might be very, you might be very inclined to do this directly, but then you can quickly fall into the trap of saying this is obvious or something like that. So again, I'm going to do it by contradiction. So let's suppose that A is not a subset of B, right? So if A is not a subset of B, that must mean that there is some element in A, which is not in B. Yes, very good. So this implies that there exists an element in A, which is not in B, right? So like formally, this means, right, formally, again, reasoning from first principles is probably enough. This means that there is some element X such that X is in A and X is not in B. But this looks very familiar, right? So in this case, this proof is just going to be a mirror image of the previous one, right? More or less. So X is in A and it's not in B. Well, this implies that there exists an element X such that it's in, well, what's the definition of a different B? It's, any element that's in A but not in B. So that means that X is going to be in A different B, right? So I have an element in A different B, but this is a contradiction. Why is this a contradiction? Because I assumed here that A different B was empty. So the definition of the empty set is that there's nothing in it. It's a set. For sure, it's a set. It's not nothing. A lot of people like to say that the empty set is nothing. It's not true. It's a set. It just doesn't contain anything, right? But here, what I've sort of arrived at in terms of conclusions is that there is actually something in A different B. And so that's a contradiction, right? That's a contradiction, which means that the initial assumption I started with, which was that A was not a subset of B, was false. Okay? So I've shown 1 implies 2, and 2 implies 1. So this implies that 1, if and only if 2. Okay? Is that good? Nice. 2 nods this time. It's good progress. All right. Let me know if I'm scrolling too fast. Another thing that we like to do in Comp 330 is to sort of quantify infinities. So in Comp 330, the other thing we like to do is to quantify infinities. Okay. Yes, very good question. It's a very vague statement. What does that mean? So the sort of high level thing that we're typically going to see more towards the second half of the class is we're going to see statements like this infinity is bigger than this other one. So we're going to say statements like that, okay? But the reason why actually we're going to say statements like that is because remember the point of this class is, is this thing possible or impossible? So actually you can directly relate this to saying something like this impossible is harder than this other one. So we're going to see that we have maybe 2 classes of problems. Both of them are kind of impossible, but one is more impossible than the other. And yeah,
What does it mean by when this other one? How do you define infinity?
yeah, good question. Yeah. So like this is very hand wavy. I agree. So how do we actually talk about this more formally? So that's why we introduced this notion of like cardinality of sets. Okay. And so cardinality of sets is very well defined when the set is finite. When the set is infinite, it starts to become a bit more blurry. And so that's why we need to introduce a sort of new notion. So if I have 2 sets, A and B, right? And both of these are infinite sets. Right? So there's an infinite number of elements in each of these. There's no bound on the size of the sets, right? So this just goes on forever. Then what does it mean? First of all, we'll start with the sort of maybe the easier notion. What does it mean for the sizes or the cardinalities of these sets to be the same, right? So what does the cardinality of A equal to the cardinality of B mean? It means that I can define, right? So this means I can define a function f which is a bijection. So it's onto and one-to-one, which maps elements of A to B, right? So bijection, if you've forgotten or you're a bit rusty, essentially means that you have a function f, right? Which for each element in this set A, maps it to a different unique element in this other set B. Okay.
Should be unique.
If you have two elements in A, right, that are different, then it must map to two different elements in B.
That's going to be subjective.
Injective, yeah. Yeah. So remember F is a bijection. Right? So F is a bijection literally means that you can kind of put the elements of the two sets in kind of rows, and there's going to be sort of a one-to-one thing between the elements, right? And so it's a bijection formally if it's injective. So for every pair of elements in A, if those two elements are different, then this implies that they map to different things. That's injective, right? So that means that you ensure that if you have two elements, then you go to different places, right? But also, right, for two sets to be of the same size, for two sets to be the same size, you also have to hit every single element, right? So you also need the function f to be surjective, which means that for every element in B, there exists an element in A such that f of A is equal to x, right? So this means that you cover all of x, or sorry, f covers all of B, right? So you hit every single element in B. And this means that f does not use the same element in B twice, right? So you don't have something like two elements in A and then one element in B, and both of these go there, right? Because that would be bad if you were trying to show that the two sets are equal, because then that's not guaranteed. Because maybe you can have all of the elements, right? Maybe you can have all of the elements in A mapped to a single element in B. In which case, there's no guarantee that the two sets are the same. Or not the same size or cardinality.
So if you have two elements in A, which point to one element in B,
Yeah.
that will be subjective compared.
I mean, it doesn't, so the question is, if you have two elements in A and it maps to one element in B, does that mean that it's surjective? So it means that it's surjective only if there's one element in B.
Yeah.
If there's another element in B, right, and it doesn't get hit by any of the elements from A, then it's not even surjective.
But for all x's and
That's right. Yeah, for all x. Yeah, exactly. Okay. So those are the two definitions for a bijection, right? And the result of the bijection is that you have these two sets that sort of couple pairs of elements together. So that's why they're sort of the same size. Okay. So that's great, but the statement I said here, right, is we're going to be showing that one infinity is bigger than the other. So how do we do this, right? If I have two sets A and B, I have some elements in A and then some elements in B, right? For A to be strictly less than B in terms of size, that means that whatever F you can come up with, you're always going to miss part of B, okay? So this means that whatever F you come up with, always miss part of B, right? So you can never get all of B mapped from A. So that just means that there are just too many elements in B, and whatever you do, your F just can't handle that, basically. So, you might design one F, and maybe it takes each of the elements in correspondence with elements in B, so it's injective, but it doesn't hit maybe this element for F1. Then maybe for F2, you can do the same. You can hit maybe these elements, but then you miss this one, right? And sort of so on, right? So more formally, what it means for the cardinality of B to be strictly greater than the cardinality of A, it means that, so formally, it means that there does not exist a surjective function from A to B. Okay. So this is to define the definition of the cardinality as being strictly less than. Okay. Okay, I was gonna ask, does this make sense? I think it would be easier if we looked at an exercise, and then I think I might be able to explain it a bit better. Okay, so this is sort of the formal definition. Let's look at an exercise where we actually apply this. Okay, so we're gonna do again problem set 1, but now we're gonna do exercise 5D. So in exercise 5D, we want to show that if you take a set A, right, and then you take its power set, right? So the power set of A is a set of sets, and each of the sets in the power set of A are subsets of A, right? And we want to show that the cardinality of the power set of A is strictly greater than the cardinality of A. Okay. So just a quick reminder before I give you a bit of time to think about it. If I have A is 0, 1, right? And just a reminder, what is like the power set of A? The power set of A is a set of sets, right? So, and all of those sets are subsets of A. So I know that the set that just contains 0 is a subset of A. The set that just contains 1 is a subset of A. The set 0, 1 is also a subset of A because A is a subset of itself. What is the other set that I'm missing? The empty set, yes. Very good. The empty set is a subset of all sets, of any set, right? Because a subset is, well, everything that's in A is also in B. Well, there's nothing in the empty set, so vacuously, it's true that it's sort of contained in B. Okay. So what we want to show is that we always have this. So you can notice here that the cardinality of A, because it's finite, I can sort of compute it directly. I can just say, well, the cardinality of A here is 2. And then the cardinality of the power set of A is 4. So we have a greater than here, right? Okay, so this is true for finite sets. But it gets a bit trickier when we deal with infinite sets. And so that's where I'm going to sort of try to let you think about it. So this is definitely true for finite sets. But what about, well, let me just say, it's definitely true for finite sets because for finite sets, we have this relation that uh, the size of the power set of A is 2 to the size of A. Okay, so you're always sort of, and this is sort of just like counting argument because you're saying, well, is each element in A in the power set in one of the sets in the power set or not, then you get sort of a branching factor of 2 and get something like 2 to the n. Right? So this is why it's definitely true for finite sets. Now the question is for infinite sets, what happens? Okay, so give me a second. This is actually quite a difficult problem. So I just want you to think about it a bit. Then I'm going to show you the general trick for solving this kind of question, and then you'll see that you can maybe just reuse this kind of trick if it's ever asked of you again. So I'll give you 2 minutes. And yeah, you have a question?
Show that our analytic set is really power of current, the analytic power set of A. That's not true. It should not be strictly small, right? It should be strictly small, because the empty set will get the same result. And two will have one. Exactly, so AC1 is smaller than that.
Hi. Okay, I have a very good question here. So I have A is the empty set. What is the size of the empty set? Very good. I have the power set of A. What is the power set of A? Aha, it's the set that contains the empty set. Aha. What is the size of the power set of A? Aha. So yes, the strict inequality is 2. Okay. Okay, well, what about infinite sets? We're just trying to show, okay, we're trying to show this, right? For infinite sets. So then for infinite sets, we're trying to show that there does not exist a surjection f from A to power set of A, right? So I mean, to get you started, like, I mean, you want to show that there does not exist a surjection from A to the power set of A. Well, what would happen if there was a surjection, right? Okay, so try to think from there. Hmm. Right, so this is, if this is greater than or equal to this, there is a surjection. But if there's no surjection, then it's the sort of negative. So the negative of this is, yeah. Let's see, the solution is great. All right. So do we have any ideas first? Okay, I don't blame you. If I were you, I wouldn't have any ideas either. Okay. Oh, yes. Idea, yes. If there's a surjection, then something weird happens, right? Right. Yes.
Can we have a function?
Okay, wait. So let's do this together. So for contradiction, suppose there exists some function which is a surjection from A to the power set of A. Right? Okay, I'm with you so far. Is everyone so far so good? Right? I want to show that it doesn't exist. So, for contradiction, let's assume that it does exist. Okay, I like this. Good start. We can map. Sorry. Can you say that again? Mhm.
To a set containing only that element.
Interesting. Yeah, I see where, okay. Okay, this is you're on the right track. So, can you explain what are you trying to do more or less? Like,
Can we resolve like every element of A for a unique input?
yeah.
You see the pasting.
Something left, right?
And the power set.
Yeah. So this is, I mean, this is a good intuition. So I think you're doing it maybe like a sort of a direct truth, right? You're saying, okay, whatever I do, I'm always going to find like some place in power set of A that's sort of not hit. So I think that's a good start. But it's going to be a bit tricky to sort of convincingly argue that you're never going to get that element. Yeah, let me show you something. Let me move this along just a tiny bit, and then show what goes wrong if you do something like this. So let me just go. Yeah, you can ask after. Okay. So okay, yeah. So let's say there was one approach. So approach one was trying to argue directly. I think the reason why maybe arguing directly would be difficult is you're always going to find like an edge case. It's going to be a bit tricky, you'll see. Like if you try to go down that route, then you'd find lots of edge cases. Okay, so maybe another approach. Let's think. Yeah.
So if say that we have a set which contains just 1 and 2.
Yeah.
So the second set which like will contain like 1, 2, 1, 2 and an empty set. And then we can see that in B. So like if we have, for example, a set 1, 2, like so that maps to 1 and 2 both. So the rest 1 and 2, like which are the separate numbers, they can't map to anything. Because the set which contains 1, 2, like is already being mapped to 1 and 2 numbers. Like if this makes sense.
I see. Yeah, to be honest, this kind of feels a bit, it's like the same vibe as approach one. It is a bit of a direct. I think what is good that you're trying is you're using a concrete example. So I think this is also a very nice thing. Concrete example.
So like we can state that there are elements in the second set.
Yeah.
Which are not by any elements in the first set, which contradicts the
Yeah.
exact definition.
Yeah,
So
yeah,
then
yeah.
it's, like
Yeah. I see what you're saying. So I like these are all the right ideas. It turns out that this is kind of an argument that's very similar to the diagonalization argument that you might have seen already. So if you don't know about it, I'll show you. But essentially, this has a flavor of, so this is in the same line of reasoning. as well, the formal name is Cantor's diagonalization. Diagonalization technique. Okay, so what does this actually look like? So I'm gonna continue from sort of this assumption. Suppose that there's a function which is a surjection from A to the power set of A. Okay, so these were good attempts, but let's see. Then what does this mean? There exists a function f, which is a surjection. So that means that for every element in the power set of A, there exists an element in A which hits it, right? Such that f of x is equal to y, right? So this is by definition, yeah? And the one thing that I just want to make you notice is that x is just an element and y is a set, right? So this is going to be relevant very soon, okay? Now, what?
This is one question.
Uh-huh.
Can one x map to two elements in inside the
Then it's not a function. Yeah, yeah. Yeah.
so
Which part? Which part? Uh, sorry, this line? Oh no, I was just writing down the approaches of people. So yeah. Okay. So y is a set, okay, and x is an element. So what I'm going to do now is I'm going to construct a y that's in P of A, okay? And I'm going to show that if there was an x such that f of x was equal to y. So I'm going to construct a particular. Then there's no better way of saying this. Something weird would happen. So namely, I get a contradiction. Okay. So what is this set going to look like? So I'm going to define it here. So let's define the set B as a subset of A. So all of its elements are in A. But all the elements in B are only in B if that element is not in f of A. Okay? So remember f of A, so this f, this is the same f as over here, right? And f of A returns a set, right? So I have an element, I give it to a function, it gives me a set. So then it's very fair game to say, well, given that element that I just fed the function to, is it in the output as well, right? So I can ask that question. And now I'm defining B as all the elements where if I give that input, then it's not in the output, right? So let me give you an example. So for instance, suppose A was 1, 2, 3, right? Then 1 is in A, right? Now suppose that f of 1 return 2 and 3, right? Then 1, right? 1, this element, is not in f of 1, right? It's not in this set, right? Okay. So that means that this implies that 1 is not in f of 1, right? Because f of 1 is just 2, 3. So this implies that it like follows this definition, right? So because it follows this definition, it means that 1 is in B, right? By definition. Okay? Is the construction clear?
How do you define B, like, how do you get the idea of defining B like this?
Yeah, so that's what I'm saying. Like if you don't know this trick ahead of time, it's actually quite difficult to come up with. Yeah, so that's why like if you had just walked out of your analysis class and you had looked at where did I say it? Cantor's diagonalization technique, then that's maybe the only way that you would have thought of this. Okay, so that's why it's kind of hard. But that's why it's important for me to show you this technique so that if it comes up again, then you can sort of identify it and just reuse it kind of symbolically. Okay. So, so this is what the definition of B is. Okay. Now, why is this useful? So B contains, so it only contains elements from A, right? So by definition. So that means that B is a subset of A, right? And if B is a subset of A, that means that B is in the power set of A, right? Just again, by definition. So that means that B is one of the outputs of the function y, of the initial function y over here, right? So therefore, B is an output of the function f, right? So it must have an input, right? So then suppose the input to f, the get B was x, right? So that is, suppose f of x was equal to b, right? So there's a lot going on here, but really, essentially, the only things that I've done is, because I can see that maybe it's a bit confusing, is I've said, okay, I have a function f, which is a surjection. Okay. Now I construct this set B. So this is like step 1 of the proof. Step 2 of the proof is I define this function. Then step 3 is I notice it's in P of A, right? So that means, right, let me answer all the questions at the end. So that means that if it's in P of A, it gets mapped from A, right? So that means that I can conclude this for. So I can conclude that there exists an element in A such that f of x is equal to B. Okay. So I've not, like, it's not, I've just said, you know, define a surjection. Here's a subset of A. Because it's a surjection and subsets are what I map to, then I have something that I map to that subset, right? I've not done anything fancy. But what I've sort of created is a contradiction. So now for the sort of weird part. So the weird part occurs here. And it's, you know, if I ask if f of x gives me a set B, well, I can just ask, you know, is the input x in f of x, right? So is x in f of x? Okay. So, I mean, suppose it was, right? Suppose x was in f of x, right? Then it means that x is in B. But if x is in B, it means that x is in the set where all the elements in that set are not in f of A. So now there's a bit of a problem, right? Because I say x is in the set, which means that x is not in f of x. Right? So that means that x is not in f of x. But I just said a second ago, x is in f of x. And this somehow implies that x is not in f of x. So then something's going wrong here. It must be that x is not in f of x. So x is not in b because f of x is just equal to b over here. But if that's the case, then that means that x is not in A in this set, right? Which means that it doesn't satisfy this condition. So if it doesn't satisfy this condition, it means that x is in f of x. But I just assumed that it wasn't, right?
So is it a fix or no?
Right. Well, I mean, we have a big problem. We have x is in f of x if and only if x is not in f of x. Well, that's impossible, right? This is clearly a contradiction. You can't be both in the set and not in set, even if you're thinking of like quantum theory. It just doesn't work for sets. So we have a contradiction. Okay. And so, yeah, that's what I said. That's what I said at the beginning. This is difficult if you don't know the trick. But once you see the trick, then what's going to happen is this is going to be shown again in the lecture, and you can basically just do pattern matching. The function is going to be an algorithm instead. X is going to be a problem, and then you're just going to sort of plug and play, basically. Okay. So it's also a bit important. So it's actually quite difficult to digest this whole proof in one sitting. So make sure to reread it a couple of times and also to come to office hours if you still don't get it.
So what does this prove that?
So this proves, right? So the conclusion is that there does not exist, because the reason why we got to this the contradiction is because we assumed there existed a function f which was a surjection. So this means that there does not exist a function f which is a surjection from A to power set of A, right? So that means that whatever you do, you're always going to have part of power set of A that doesn't get hit, right? So you always have more elements in the power set of A than A, right? So then that's how we conclude this result. Okay. Okay. So, like I said, a bit of a difficult proof to digest. It's going to come up again in the second half of the class, so I just wanted to prepare you a little bit. But please feel free to ask me at my office hours or the TA's office hours. Okay? Okay. So we're going to finish the tutorial with something a bit more concrete. We're going to switch gears and talk about alphabets, strings, and languages. Okay, so I'm going to go through this a bit quickly so I can get to the actual exercises. So like an alphabet is just a collection of letters or symbols. So we typically define this as sigma, and you have maybe like 0, 1, or something like AB. Right? So these are very common in Confu 30. Then from alphabets, so from sets of symbols or letters, you can create strings. So strings are just sequences of symbols or letters which are from, the alphabet. Okay. So for instance, one string might be 0, 1, 1, 0, right? If the alphabet is 0, 1. And then another string might be 0, 1, 1, right? These are two strings. What's not a string, if this is the alphabet, is maybe something like A, B, 0, right? Because these guys are not in the alphabet, so this is not well defined. Okay. It's as if you didn't have that on your keyboard. You can think about it that way. Okay, so I have strings, and then there's different properties of strings. So the strings have properties. So you might define length of strings. So the length of string is just the number of symbols in that string. So number of symbols in W. So in this case, if I look at this string, that's 4, right? So I have 4 symbols in my string W. I can also do something like concatenation. So I can take the string W and the string S and then place S right after W. And that's just concatenation. And typically we represent this with a dot. So the result here is 0, 1, 1, 0 dot 0, 1, 1. In the end, that's this string, which now has length 7. Okay, so I'm just sticking the two strings together. The other thing is we have this notion of the empty string, which, like the empty set, is not nothing. It's a string which has length 0, right? So it's a string with length 0, and it's typically represented as epsilon, especially in this class. Okay, and then the last two operations, there's the string exponentiation. So in strings exponentiations, you're essentially just doing some kind of shorthand for concatenating multiple times, where, for instance, W power n is just W concatenated with itself n times. Okay, and by definition, W power 0 is the empty string. So you can define this like inductively, but I'll save you the details and just, I think the intuitive definition is good enough. And then the last thing is you can also do stuff like string reversal, where you just reverse the string, right? So instead of reading it from left to right, it's as if you're reading it from right to left. So the reverse of W, if W is 0, 1, 1, 0, is in this case, well, I'm reading it 0, 1, 1, 0 left to right. When I reverse it, I have to read it right to left, so 0, 1, 1, 0. In this case, it's the same, right? In this case, the reverse of the string is the same as what you sort of started with. So here I have a palindrome. Yeah. Yeah, string exponentiation is, let me write it, when you concatenate a string with itself n times, where this n here is the exponent, basically.
So no one did it right.
This means that W to the 0 is the empty string.
So there's like a meaning message.
Yeah, so you can think about it as like, well, W to the 0 is I concatenate myself, I concatenate with myself 0 times. So as a result, I have just an empty string, right? Okay, so maybe I forgot to give you the example for this one, but for instance, if I have W to the power 2, right? So 0, 1, 1, 0 power 2. A typical mistake that some students make is they say, well, this is 0 power 2, 1 power 2, 1 power 2, 0 power 2. So that you probably get that from calculus. In this case, it's not the case that this is true, because what you're doing is you're taking this whole string and concatenating with itself, right? So that means that you get 0, 1, 1, 0 first, and then you concatenate 0, 1, 1, 0 with itself another time. So you get this string. Okay, so this is the correct thing to do. Okay, so let's do a final exercise before we end the tutorial. Let's do problem set 1, exercise 8. There's a few questions, so let's do A, B, and C. So these are a good way to wrap up, I think, because they're not as mind-bending. So I'll give you like 2 minutes again. Mhm.
Is that 1P30 or is this some division for something? Should
Like,
we expect it to like guess?
because it's very possible that you get a true false in a midterm, which is like you have this condition, is A a subset of B? Right. You have like it's very possible that you get like a true false, where it's like you have two languages, these are their properties. Is it true or false that this language is a subset of this other language?
Big garden, it's like by induction.
Yeah, we'll get to, yeah. So it might, yeah, we'll get to that. Tutorial 2. So it might be that we ask you an induction. I mean, it is theory of computation. So
So this is important to.
yeah. I'm not trying to waste your time. Yeah, exactly. Yeah,
Stay subset language, A subset language.
yeah.
Every skills of language.
That's right. That's right. That's right. Yeah. Okay. So, like I said, hopefully this one was a bit more concrete than the previous question. So if we start with A, right? W is AB. The string W is, well, in this case, the alphabet is also AB. The first string W is AB, and the second string V is BA, right? And we're asked to just compute this operation, W square, V square, W0, right? So first things first, W0, that's the empty string. So W square, V square, concatenate the empty string. So there's this property of the empty string that, if you take a string and you add the empty string to the end of it, then it stays the same string, right? Because I'm not adding any symbols to it, right? So then that means that I get W square, V square. And now I can start replacing. So W square is AB square. And then V square is BA square, right? Now, again, remember, don't fall into the trap of, something like ABN is ANBN, right? Very common mistake. So remember, AB square, AB whole square means you take AB and you copy it once, right? So it's AB concatenated with AB, right? And then BA square is BA, right? And then these two things are concatenated together. So then if I just remove the parentheses and all the dots, then I get the string AB, BA. Okay, good. Okay, good. Then I think I gave everyone the problem sets. I don't have one of my own, but I think the other question is, well, what is the length of W square, V square, W0? Okay, good.
I have mine both.
Oh, great. Thank you. So the length, I mean, I could compute this two ways, right? I could compute the string itself and then count the number of symbols, right? So here, if I just copy this, so I'm not going to write it, but if I just copy it and I just count 1, 2, 3, 4, 5, 6, 7, 8, then I have a length 8 string, right? Or I could also just notice that I can rewrite the length of the string as, 2 times the length of W plus 2 times the length of V plus 0 times the length of W. So, this is 0, then I have 2 by 2 and then 2 by 2, which gives me 8. Okay, so there's two ways of doing it.
You can count it directly as well.
You can, sorry?
Directly as well, like the number of alphabets, it's like this.
Yeah. It's the same. Yeah. Okay. Then let's see. B asks us, oh, right. Oh, yeah, this is a good question. So W is ABB, right? And now what's happened in this question is I've introduced the notion of a prefix, right? So the prefix of a string, right, is, well, a string is a prefix of another string if it's like any beginning of that string, right? So the formal definition is U is a prefix of W if I can write W as UV, right? Where U is in sigma star, and then V is some other string in sigma star, right? But I mean, the idea of prefix is probably intuitive to everyone, right? It's like any string that starts at the beginning of the string and goes up to some point, right? So here, what are the prefixes of W? Well, A is a prefix, right? Because it sort of starts the string. Then AB is another prefix. So you go A and then also AB. And then the entire string is also a prefix, right? So ABB is also a prefix. Okay. Am I missing substring? Oh, yes, the empty string. Very good. So the empty string is also a prefix, right? Why? Because, so this is a prefix because the empty string concat ABB is ABB, right? I was able to find a string V. I was able to find a string V, which gave me W, which means that this guy is also a prefix. Okay. Yeah.
This would be proven by induction.
What would be proven by induction? Yeah. Yes. I mean, we gotta get to, yeah. Okay. You had another question? Okay. Let me quickly finish. So the actual question is, if I have a string W of length n, then how many prefixes do I have? I'm not asking you in this case to prove it. I'm just asking for the number. So, if you think of the string as a sequence of symbols, the sigma 1 all the way to sigma n, well, what are the prefixes, right? They're all the things that are sort of starting the string, right? So I have the empty string, then I have sigma 1, then I have sigma 1 to sigma 2, then sigma 1 to sigma 3, all the way to sigma 1 to sigma n. So that's one prefix here, then one prefix here, then one prefix here. So I have n here, and then the extra one for the empty string. So I get n plus 1 prefixes if my string is of length n, right? Which worked out actually over here. Okay? So uh, we haven't covered the definition of prefix in the slides. That's true. It's in the problem set though. So if ever you're given a new concept, then it'll be defined for you in the question. So like I did here. Yeah. Okay. Yeah. You mean B here? So BB, those would be suffixes. So it has to be sort of starting from the beginning of the string.
Oh.
Yeah. Starting from the end of the string. Yeah. Okay. Okay.
What would the suffixes of the B?
The empty string, B, BB, BBA.
BBA.
Well, I mean A, BB, yeah.
So BBA.
Oh, sorry. Yeah. So B, so this string, and then this string. Yeah.
And then this other.
And the empty string. Yeah. Very good. Yeah. Because you read left to right. Okay, great. So next time I'm going to do question 10 about languages, and then I'll do the FA question, like the DFA and NFA questions.
What's your
Uh, Yeah, also maybe part two, yes. Okay, great, thanks a lot. We'll all have office hours next week, so you can also come and ask us questions. Sorry? Oh, yeah, my